So we're going to talk about derivatives of what we call transcendental functions, which sounds very like New Age Sedona power vortex type stuff, but transcendental just means non-algebraic. So we're talking your trig functions, your exponential functions, and like natural log. And here you go. The derivative of sine is cosine. So there's your first one. Go ahead and write this down and then give me a green check, and I'm actually going to go back to our title slide, which kind of gives you a good visual. General idea, you know that the derivative represents a slope. So just to give you an intuition for why this is true, I can go back to that title slide. And the top graph is the graph of sine. And if we look at the slopes, right, everywhere there's a peak or a valley, we get a slope of 0. So we can just plot zeros on the x-axis at those points. And then if we take a look at what's going on in between, so here we have positive slopes that get closer and closer to 0. So you're going to have positive y values that get closer to 0. And then here, same thing. We have negative slopes that get their steepest right here. So they're most negative there, and then are still negative but approach 0. So it's pretty clear that the derivative of the sine function is still going to be a wave function, but that's slightly shifted, and it actually ends up being the cosine function. And as you can probably guess, the derivative of cosine, if we look at the slopes of this one down here, you do end up with a very similar wave function. So it is going to be related to sine. It's not exactly sine, however, but we'll get to that. So now that we know that, let's do an example. For what values of x does this graph x equals f of x equals x plus 2 sine x have a horizontal tangent? Well, we know that when we're talking about tangents, we're talking about derivatives. So the first thing we want to do is take the derivative. So f prime would then be, we know the derivative of x is just 1. Here we have a constant multiple times sine x, so we just use our constant multiple rule, which would be just multiply 2 by whatever the derivative of sine is, and we just said the derivative of sine is cosine x. All right, so there's my derivative. Now what's the value of a horizontal tangent? They want us to find values of x for which the tangent is horizontal. Yeah, horizontal tangent is slope 0. So I want to set my derivative to 0. I'm going to set this to 0 and solve. So I have 1 plus 2 cosine x equals 0. Isolate cosine, so subtract 1, divide by 2. Cosine x equals negative 1/2. All right. So this is something that we're going to have to be able to solve by hand without a calculator. So a little trig unit circle review. Remember that cosine is adjacent over hypotenuse in a right triangle, right? There are two special right triangles that I said you would need to have memorized, which is your 30, 60, 90 and your 45, 45, 90. Which one of those two triangles could possibly produce a ratio of 1/2? 30, 60, 90 or 45, 45, 90? So remember what the ratios are. In a 45, 45, 90, we have 1, 1, rad 2. In a 30, 60, 90, we have 1, 2, rad 3. Which one of those could possibly produce a ratio of 1/2? Right. Only the 30, 60, 90. So it's going to be an angle whose corresponding angle is either 30 or 60. Now the other thing we want to think about is actually we need the ratio to be negative 1/2. So now we go to the unit circle and we have to decide, okay, which quadrants would cosine be negative in? So we have 1, 2, 3, or 4. And there's some acronyms you can use that sometimes help people memorize them, right? There's all students take calculus, and each label represents which trig functions are positive in that quadrant. So in the first one, all of them are positive. In the second one, only sine is positive. In the third one, tangent is positive. And in the fourth one, cosine is positive. And everything else is negative. So this has to be quadrants 2 and 3, right? All right, and cosine, remember, is adjacent over hypotenuse, and I want my ratio to be 1/2. So it has to be 60 is our reference angle, okay? So I'm going to build a triangle in those two quadrants where 60 is our reference angle. So this is 60 here. And then this would be negative 1. And this is 2. So it's negative because we're on the negative side of the x-axis. And then there's also a triangle down here. Oh, I'm sorry. That's not 2. The hypotenuse is 2. Good. So we need to know what these true angles are. Their reference angles are 60. So what is this angle from here to there? $120. Good. But guess what? This is calculus. We deal in radians. So my answer can't be x equals 120. I need it in radians. So you can multiply by pi over 180. So what is that? 2 pi over 3. What about this angle from here to my other reference angle? You can give it to me in radian or in degrees. We'll just have to convert it to radians. So that's going to be 240 degrees, right? So we'll do 240 times pi over 180. Just divide out the 60, and we get 4 pi over 3, right? Good. But those aren't the only angles. Because any coterminal angle, so if I went all the way back around, so I added another 2 pi to that, right? That would also be a solution for both of these. So I'm going to create an answer by establishing a pattern. So x equals 2 pi over 3 plus 2 pi n, comma 4 pi over 3 plus 2 pi n, where n is any integer. And that just establishes that, yeah, we could go all the way around for both of these and come back and be at a new coterminal angle, and that would also be a solution. All right, so let's look at what we established graphically real quick. So our function was x plus 2 sine x. It's a pretty weird looking function. Kind of what you would expect it to be though, right? We're kind of combining a linear function with a sine function. So this almost looks like a sine wave traveling up a linear function. And we found at each point where the tangent was horizontal. And so we said that one of those solutions was, what, 2 pi over 3? Oh, whoops. So to be able to do that, I need to do 2 pi over 3 comma f of 2 pi over 3. Boom. Right there, the tangent is horizontal, right? And then we said 4 pi over 3. And that's going to account for all these valleys. And then anytime I add 2 pi to point A, it's just going to move it up to the next peak. And anytime I add 2 pi to point B, it's going to move it over to the next valley. And at each of those peaks and each of those valleys, we'll have a horizontal tangent. Does that make sense? All right, give me a green check if we're good with that example. Go ahead and ask if you have any questions. Vincent, are you paying attention? All right. Well, I said the derivative of cosine is related to sine. The derivative of cosine is just negative sine. So the derivative of sine is cosine, and the derivative of cosine is negative sine. Give you a second to write that down. Give me a green check when you're done, and we will move forward. So we have a situation where we have an object at the end of a vertical spring, and we stretch the spring basically downwards 4 centimeters beyond its rest position, and then we release it, right? And so what the object is going to do is bounce, right? Back and forth. And so its position at time t is given by the function 4 cosine t, right? Which is a wave function. It's oscillating. And we want to find the velocity and the acceleration at time t, and then we'll use them to analyze the motion of the object. All right. Well, if we're given position, we've already discussed this a few times. The derivative of position is velocity, right? All right, so what would the derivative of 4 cosine t be? Well, we know from this last slide that the derivative of cosine is negative sine. So it's going to be negative 4 sine t. That's my velocity function. And we also know that the derivative of velocity, which is the second derivative of position, is acceleration. We know from our first slide that the derivative of sine is just cosine. So this is going to give me negative 4 cosine t for the acceleration. All right, And so now let's talk a little bit about what they say, analyze the motion of the object. What I want to know is when it's speeding up and when it's slowing down and when it's changing direction. So how is velocity different from speed? What does velocity tell us that speed does not? There, I've asked it in a way that you can give me a one-word answer if you'd like to. Perfect. Direction, right? So the sign of velocity tells us direction. So the velocity function is the thing that'll tell us about when it's changing direction, correct? How do you know when an object is speeding up or slowing down? What tells you about when an object speeds up or slows down? Okay. So the misnomer, the common fallacy is that it's acceleration. Acceleration does tell us the rate that velocity changes. But it's not just acceleration. It's both the comparison of acceleration and velocity. So I always like to do this. Think of throwing an object into the air. The object that you throw into the air, this marker takes two trips. It goes in two directions. It goes up and then it comes down. What's it doing when it's going up? Is it speeding up or is it slowing down? It's slowing down. And that's because the object's velocity is in contrast to its acceleration. The signs are fighting against each other. When it's going up, its velocity is positive. But what do we know that the acceleration due to gravity is? Approximately what is it? Negative 9.8, right? Meters per second squared. So when an object has a positive velocity but a negative acceleration, those two things fight against each other and that causes it to slow down. But what's going on with my marker when I throw it in the air? As it comes down, is it speeding up or is it slowing down? It speeds up. The reason being its velocity is negative and so is its acceleration, right? So to tell if an object is speeding up or slowing down, you need to compare its acceleration to its velocity. If the signs are in agreement, it speeds up. If the signs are in disagreement, it slows down, right? So let's look at, I want to look at the graph of this function. Both the position, the velocity, and the acceleration. And I'll pull up GeoGebra. Got to share that with you. So our function was what? Our position is 4 cosine x. Yeah. All right, so there's my function. That's the position. There's the velocity. There's the acceleration. All right, let's get rid of the position for now. We'll just look at velocity and acceleration. Velocity, I guess, is the orange. Acceleration is the purple. Sun's colors. So let's just look at time. That's going to be like 0 to pi over 2. So from 0 to time pi over 2, right? So here to here, is my object speeding up or slowing down? So it's going to be both velocity and acceleration from 0 to whatever that is, which I think is pi over 2. The velocity is negative, and all the y values of acceleration are negative, right? So velocity and acceleration agree, it's going to be speeding up. Now, once I get past here, from like here to here, which is going to be pi over 2 to pi, So here to here, in between those two vertical lines, notice that the velocity is negative, but the acceleration is positive. So over that time interval, time pi over 2 to time pi, my particle is slowing down. Does that make sense? So this is all in a vacuum. This is like in the vacuum of space. Because in reality, we have things like friction, and it wouldn't just keep bouncing up and down. It would eventually slow to a stop. But without friction, if this spring just kept bouncing up and down, it would go between slowing down and speeding up constantly, right? Indefinitely. All right. So we're done with that example. Let's move on. Okay, find the 27th derivative of cosine. Any guesses? Well, we know that the first derivative of cosine is negative sine, right? Then the second derivative would be, derivative of sine is cosine, but I have a negative out front, so it would be negative cosine. Then the third derivative, the derivative of cosine is negative sine, but I already have a negative out front, so it's going to be positive sine, right? And then after 3, we kind of get rid of prime notation and just put the number in parentheses. So the fourth derivative is then we're back to cosine, right? So we're back to start there. So you can kind of figure this out by going, okay, so every 4 derivatives, I'll just be back to the original function, right? Well, what's 27 divided by 4? So if you divide 27 into 4, you're going to get 6, and you're going to have a remainder of 3, right? So once we take 24 derivatives, we'll be back to cosine x. And then we just need to take 3 derivatives again. What's the third derivative of cosine? Sine, right? So, yes, I agree that the 27th derivative of cosine, which we would notate like that, is sine x. All right, give me a green check when you're good on that one. The definition of E is a natural constant like pi. It's irrational. And it can actually be defined many ways, but the calculus definition is this. It's the number that satisfies this limit. And what you can recognize that limit is the derivative at 1 for an exponential function specifically. It's the exponential function whose slope at 1 is 1. And more than that, something very interesting about E is that its y values actually are equal to its slope at that point. Meaning the derivative of e to the x is just e to the x. All right, so e to the x is an interesting function that's exponential growth. It's about 2.72. And it's a function who, wherever you look at its slope, the y value at that point is actually equal to the slope. So if I look at f of 0, I get 1. So the slope at 0 equals 1. If I look at point 2 comma f of 2, so that's e to the 2. I get like 7.39, so that's saying the slope of the tangent at that point is 7.39 as well. All right, so let's do one more quick example with e to the x, and we'll save logarithms for next time. All right, so here's a good example that'll tie in the stuff we did last time. So we have y equals x squared times e to the x, and it says dy dx equals, so we're looking for the derivative. That's it. We'll note that this is a product, so we're going to have to use the product rule, right? So remember what the product rule is. If I think of x squared as f and e to the x as g, then remember that the derivative of f times g is fg prime plus gf prime. So here I would get, let's see, x squared times the derivative of e to the x we just said is e to the x plus gf prime e to the x times 2x, or x squared e to the x plus 2x e to the x. That is it.